So, hello and welcome to a lesson about simple harmonic motion, or SHM. And I will summarize what we know about displacement and most of all velocity and acceleration. And then I will show you one exercises how you can work with it, just very short. So, okay, let's draw a diagram that shows this motion. So I have the time axis like this, and on this axis, the y-axis, I will have three things. I will have the displacement that shows the distance from the equilibrium line. I will have the velocity, and I will have the acceleration. But I'm start with the displacement, the distance. So I will make some marks like this. No, sorry. Skip this. Every third square. So let me see if I can draw it. So the object that, for instance, is attached to a spring and it goes up and down like this. Then you could describe it with the sine curve. It will look something like this. It goes up and it goes down. It goes up and it goes down. And you see this typical sine curve like a snake. And this is the graphical representation of the motion, the displacement. With an equation, it looks like this. The distance or the displacement is equal to the amplitude. And the amplitude is the highest displacement. You could call it capital A as an amplitude, or as they wanted in this book, it's x0. So x0 times sine for the angular frequency multiplied with the time. You have seen it before. The displacement depends on the amplitude times the time, times the sine for the time, times the angular frequency. And this is a constant and this is a constant. So the displacement depends only on the time in this case. This is true when you start and taking the time for the motion when the mass attached to the spring is going upwards. It starts going upwards. So I'm writing here center and upwards, because it could also start here and going from the center and downwards, which could start here as well. I will show you that quite soon. Now, the velocity for this. So this axis is for three quantities: displacement, velocity, and amplitude. So the velocity, I use the same scale, so the maximum velocity will be the same as the maximum displacement. It don't necessarily has to be in that way. So when the masses passes the equilibrium, the velocity is the greatest. It's positive, it's on its way up. And after time, it's zero. It stands here and it's turning here and it's going down again. Here, the velocity is at highest, but with a negative value. And then it stands still here at the bottom again. So we are here. So you see, we can connect these points with a line. Highest velocity, it stands still. The lowest velocity, and here it stands still again. So I connected these dots and it's the same sinus curve. But this curve is the differentiated curve for the sine curve. And from maths, you know that the velocity then is x0 times the inner differentiated derivative for this. That is omega times cos for omega t. And you need a negative sign because the derivative... No, sorry. Oh, don't listen to me. Not any negative signs here yet. The derivative for sine is a positive cos, so that this is true. I'm so sorry. Now, let's look on the acceleration. Okay, so the velocity is going upwards, but you can see the gradient of the line is immediately going down. That means that the velocity is decreasing. So we need a negative acceleration that increases all the time. And here at the top, the object, the masses attached to the spring, has the greatest resultant force. Therefore, the acceleration is the greatest towards the other direction. So I make a point here to show that. At the top here, the acceleration is downwards. That is a negative value because upwards is positive. The acceleration is 0 here at the equilibrium line because there are no resultant forces here. So here, no resultant forces, it has to be 0. Here, the spring is stretched the most, therefore the resultant force is the greatest and positive because it wants to draw it back up again. So I make a point like this. Now I attach them together, I connect them together, and it looks something like this. Now let me see. It's this curve I have to look for. Here, the force and the acceleration has to be 0 because it is at the equilibrium here. Then there is no resultant force, so it goes back like this. Now we have to do like this. I do this and show that this is the displacement curve. And the ones that goes down here is the velocity curve, and the one that starts at the other direction is the acceleration curve. Okay, I continue with this, and at the maximum displacement, the acceleration is the most positive at the other direction. The resultant force is at the highest here, so the force wants to turn it back from this point. Therefore, it's negative. And then it continues to go like this. So there are many curves now. But let me show you this. Let's look at this acceleration curve and the displacement curve. They are always the opposite, like this. So the acceleration is the derivative of this curve. So let's derivate or differentiate. Then I will get x0 with a minus sign because the derivative for cos is a negative. Omega squared times sine for omega t, like this. But we could also write this as, now you see, x0 and sine omega t, it's the same as this. So that is x. I write an x. And we have omega squared and a minus sign in front of it. So we see that the acceleration is proportional to the displacement. The greater displacement, the greater the acceleration. That's how you get a simple harmonic motion. It has to be in that case to get a simple harmonic motion. Okay, now let me show you this. This is the displacement. The maximum displacement, x max, is x0, the amplitude. You know it already. What is the maximum velocity? V max. Well, you see, if the x max is x0, that's happen when this part is 1. Because you know from maths, the trigonometry lessons, that the sine function has its maximum, and that's 1. And when it's 1, we have the highest value for this. That is x0. And that's the same thing for cos, the cos function. The highest value for it is 1. So the highest value for V max, the highest value for velocity, is x0 times the angular frequency. x0 times omega, like this. And at the same argument, with the same argument, the maximum acceleration happens when the sine function is 1. And then we have left minus, I start with omega here, squared times x0. So we have a max value for all these, a maximum value. Now, if I would like to calculate a value, not just the maximum value, but any value for the velocity, then I need these two constant, but I also need a time. But sometimes, and in this case, you will not get a time. You will only get the displacement. And if you have the displacement and you also need the amplitude, then you can calculate a time with inverse sine function. It's a little bit complicated. And then you can put in the time here. But there is a shorter way, and I will not show you the reason for it. You can find it in the book. But there is another way to calculate the velocity. And that is, you take the angular frequency and you multiply it with the square root of x for x0, or the amplitude, squared minus the displacement in that exact moment where you want to find the velocity. That is, if you want to find the velocity when the displacement is like at this point, what is the velocity? Well, first of all, I have to find the curve here. If I have the curve, I can just read it on the axis. But if I want to calculate it, I need this formula. I find the displacement. This is a constant, the amplitude, and this is the constant, depends on the period time. Then it's possible to calculate the velocity. We will do that today. Okay, now to make it a little bit more complicated, but not that very complicated, but I will show you one more thing here. So we have a timeline. We have the displacement, the velocity, and the acceleration. So here we have this displacement curve. Now, there is not a law that says that we have to start the time here when the motion is going upwards, from the center and upwards. We could start a time here when it's at its top. If I do that, it will look like this. It will start at the top. I mark every third squared like this, and then it will start with going down. and then it will go like this, and then it will go up again, and then it will go like this, and then it will go down again. So this is the same curve, but instead of starting with going up, it's going down. It's okay to let it do that. This is the displacement curve. But if we do it in that case, then the acceleration will do the opposite, in some sense, curve. So the acceleration will look like this, going this direction, going like this, whoops, going like this, and going like this. So this is acceleration. And finally, the velocity curve will look like this. It will go in this way, and then it will go this, and then it will go this, and it will go this, and it will go this. So this is called that we start with maximum displacement. So instead of center upwards, we start at its maximum displacement, and it can only go down then. Then the function looks a little bit different. So you see, if you start at its top, like we started at its top with the velocity here, it becomes a cos function. So in this case, the displacement x is x0 times cos for omega t. So instead of sine omega t, it's cos omega t. That's perfectly fine. But then the velocity will be, now it will become a negative here, because the derivative of cos is negative sine. And then we have x0 omega sine omega t. And the acceleration is negative x0 omega squared and cos omega t. You can have brackets here to be very clear here. The maximum velocity is the same, and the maximum acceleration is the same, and the amplitude, of course, is the same. And you can calculate the velocity at the same way. It's no difference there. Okay, you have these in your formula booklet, at least these, not the maximum values. And you have these as well. You have to just understand if it starts from the center and going upwards, or if it starts at its maximum and going downwards. Okay, just one example on this now. So, it looks like this. Example. A pendulum swings with SHM. That is, it swings with simple harmonic motion, as a simple harmonic motion. And a time period of 2 seconds and a amplitude of 4 decimeter. Now, a pendulum, that is what you call when a mass is attached to a spring and it goes up and down. But it also a pendulum when you have something going like this in gravity, like an old clock in your grandparents' house maybe. Then it is a pendulum. And if you look at the top of the pendulum, the bottom of the pendulum, it describes a simple harmonic motion because it's going fast here at the bottom and it stands still here. and then it's going fast, and then it stops, and then it goes backs and forwards like this. So that's a simple harmonic motion. You can describe it with a sine curve, the distance here. If you look from this perspective, if you have your eye here, it goes up and down just, and you don't see it goes in a curve like this, just going up and down. Now, the question. What is the velocity 3 decimeter from the maximum displacement? And that is a question. And if you would like to try first, you can take a pause now, and then you can come back and see if we've done it the same way. But it's on these exercises, it's always some of these formula that you would use. A hint, it's this formula. So I will show you now. What is the velocity? So something with velocity. I could try use this formula if I want to. So x0 omega cos omega t. This is the formula for velocity. But I have a displacement value. And this is the amplitude. I have the amplitude, but I don't have any variable for the displacement here. But we know another formula now for velocity. It looks like this. Let's write it down. Omega and the square root of x0 squared minus x squared. And we can use that. But now we have to find x. What is the displacement? Let's see. What is the velocity? 3 decimeter from the maximum displacement. Well, if it's 3 decimeter from its maximum displacement and the amplitude is 4 decimeter, then x, the displacement, is 1 decimeter. Because if you're 3 decimeter from 4, you have to go 3 decimeter away from it, then it's 1 decimeter left. Okay, let's see if we can calculate it. And now we have to remember that the angular frequency is 2 pi divided with capital T. And T, we have it, it was 2 seconds. So, the velocity is 2 pi divided with 2 seconds. That's the time. And I multiply it with the square root of the amplitude. But if I want it in meter per second, then I have to convert this to meter. That is 0.4 squared minus the displacement 0.1 squared. And I will have the result in meter per seconds. Let's use our calculator. So we can cancel out the 2 here. Let's see. We start with pi, and then I multiply with the square root of 0.4 to the power of 2 minus 0.1 to the power of 2. And enter. So the velocity is 1.22 meter per second with 3 significant figures. Okay, thank you for today.